funding provided by the National Science Foundation.
Hi guys, my name is Kayla and I'm a PhD student in the Materials Science and Engineering program here at UD.
Hi guys, my name's George. I'm a PhD student here in the Biomedical Engineering department here at UD, and we're both in the NRT MIDAS program.
So today we'll be talking to you about calcium alginate hydrogels, how to make them, as well as some properties of them. The term hydrogel dates back to 1894 when J.M. Bemelin first used it to describe a colloidal gel. However, the first report of applying hydrogels for practical purposes, such as biomedical applications, was given by Witterell and Lim in 1960. Otto Witterell, a Czech chemist, is credited with the creation of soft contact lenses as he successfully created the first few prototypes in December 1961 at his kitchen table, completing his patent application just a few days later. In the first 4 months of 1962 alone, they made 5,500 contact lenses. While soft contact lenses are still a major consumer product made of a hydrogel, you may also recognize Jell-O, water beads, and even some wound dressings as additional hydrogels you encounter in everyday life.
At this point, you may be thinking to yourself, what makes a hydrogel? Well, a hydrogel is described as a three-dimensional structure that swells in water. Hydrogels are often composed of water-loving or hydrophilic segments that allow them to maintain their structure when swelling due to physical or chemical bonds between segments called crosslinks. These segments are known as polymers, and they are very long chains of repeated molecules, or monomers, that are bonded together to compose the structure of a hydrogel. When making hydrogels, their mechanical properties can be varied by changing the number of polymer crosslinks. For example, reducing the number of crosslinks would result in a soft or amorphous hydrogel. However, increasing the crosslinks would produce a stiff gel. Overall, the ability of a polymer chain to form a crosslink network will ultimately determine the properties of a hydrogel. The formation of calcium alginate hydrogels can best be explained by looking at the chemistry of the system. Sodium alginate is soluble in water, and because of this, sodium ions will dissociate and become unbonded. When sodium alginate comes into contact with calcium chloride, the calcium ions will dissociate from chloride and instead bind to the alginate backbone to take the place of the sodium ions. Since calcium has 2 free electrons compared to the 1 free electron from sodium, the chains are able to form between the alginate polymers, and this allows for cross-linking of the hydrogel network to occur. And because of this, water is able to enter through the framework. Here's a schematic of the synthesis that we're about to show you.
So George is going to be showing you how to make the sodium alginate hydrogel, but first I'm going to be introducing the 2 reagents we'll be using. So this is 0.5% calcium chloride solution in water, which is a type of salt, and this is 2% sodium alginate, which is a type of polymer made from brown seaweed. So George is pouring in the 0.5% calcium chloride solution into a beaker with a stir bar. And he's just turning on the plate so that it starts stirring the solution. And now he's going to begin placing 2% sodium alginate solution into the other solution. One interesting property about hydrogels is that you can encapsulate or trap certain molecules within the hydrogel, and to show this we're using the green food coloring to show that it stays in there and retains its color. So once dropping the colored sodium alginate solution into the calcium chloride solution, the solution in the beaker will need to stir for about 15 minutes, and we have it going at a rate of 400 revolutions per minute. After 15 minutes, the beaker can be removed and the solution can be drained, leaving you with the formed hydrogels that you can make into fun shapes like the UD logo. As George mentioned, changing the number of crosslinks can change how stiff a hydrogel is. Well, we can actually quantify that stiffness. Elastic modulus, which is also known as Young's modulus, is a measure of how stiff any given material is. Thus, if we zoom out, we can look more broadly at many different types of materials. When doing so, we see that foams and polymers, which are much more flexible than metals, have a lower elastic modulus. You may be asking how you can find out the elastic modulus of a material. One method is by using a custom mechanical test that indents the material we made and sends data to a computer. Using some quick math, we are able to transform the recorded data into the known materials property of elastic modulus. Now we can see what the data actually looks like in the form of a plot. On the right, you can see the plot shows force versus how far into the material we pressed. The slope of that line is representative of the elastic modulus. When we compare that to the recorded value of Jell-O, we see that our hydrogel is nearly 3 times as stiff. Here at the University of Delaware, the process of synthesizing a hydrogel, as well as studying materials' properties such as elastic modulus, is done every day. Overall, hydrogels have many applications in the world of science, including their ability to act as tissue engineering scaffolds and drug delivery platforms for diseases. Additionally, using characterization and data analysis techniques to analyze materials' properties, such as elastic modulus, allows for a better understanding of one's experimental research and often helps direct a researcher's path forward. Thanks for watching, guys, and I hope you make some hydrogels.
Bye, everybody.
Funding provided by the National Science Foundation.